You have studied a continuous function in calculus and other mathematics courses. In this video, we're going to study continuous function from the point of view of topology or using topology. Let me give you a formal definition of continuous function, and then I will give you some examples and then other properties of continuous function. So here is the formal definition of continuous function. Continuous function okay, let's say X is a topological space with topology tau, and Y is another topological space with topology tau prime. Okay, we have two topological spaces, X and Y, with the topologies tau and tau prime respectively. Then a function f from the topological space X to the topological space Y is continuous, or this function is called the continuous function if the inverse image F inverse H is open in X for every open set H in Y. Okay, so this is the formal definition of continuous function. We have two topological spaces X and Y with their topology tau and tau prime respectively. Then a function f from X to Y is called continuous function if every inverse image of open set in Y every inverse image of open set in Y has to be open in X. If the inverse image of open set in Y is open in X, then that function is called continuous function. Okay, now let me recall you what is the open set H in Y and what is the open set F inverse H in X. Recall just the definition of open set. I'm recalling the definition of open set in topological spaces. Since now here H is open in Y if H is an element of the topology tau prime in Y. A subset H of the topological space Y is called open if H is an element of the topology tau prime in Y. And also in this definition we need this inverse image is open in X. So here this inverse image of H is called open in X if F inverse H is an element of tau. Okay, and then now here what is this inverse image of H? So inverse image of H under the function f is the set of all element in X such that the image of X under F, it has to be in H. Okay. So basically, let's say we have a topological space X, and we have another topological space Y here with their respective topology. This is a topological space X and this is a topological space Y, and let's say we have a set H in Y, then the inverse image of this guy H basically is the subset of H such that the image of this subset under F, it has to be the H. Okay, then this guy is called the F inverse H. It's basically set of those X such that F of X, it has to be in H. I'm sure you guys have seen this definition of inverse image in other lower level math courses. Okay, now from this definition you can see that H is open in Y if H is an element in the topology of topology tau prime of Y, and F inverse H is open in X if F inverse H is open in F inverse H is open in X, or F inverse H is an element in the topology tau. So from the definition of open set and from the definition of a continuous function, we can say that a function is continuous if the inverse image of each element in the topology tau prime, it has to be one of the element in the topology tau. If that is the condition, if that condition is true for this function, then the function is called continuous, otherwise not. Let me repeat one more time. If the inverse image of each element in the topology tau prime is going to be one of the element in topology tau, then that function is called continuous function, otherwise not. Okay, now let me give you some example of continuous function here. Example number 1. Let's say I have this topological space whose elements are A, B, C, and D with topology with the topology tau, whose elements are obviously empty set, whole set X, singleton set A, another set A, B, and then one more element which is A, B, C. So we have a topological space X with this topology. And now let's say I have another topological space whose elements are X, Y, and W, and Z with topology tau prime, whose elements are empty set and whole set Y, and singleton set X, singleton set Y, two element set X, Y, and then three element set Y, Z, and W. So we have two topological space with their topology tau on X and the topology tau prime given by this collection on Y. Okay, so in the first part of this example, let's consider a function X to Y, which is defined by the image of A under F is Y, image of B under F is Z, and image of C is W, and image of D is Z. So basically you have like this. Okay, here let's say this is my topological space X and this is my topological space Y, and the elements of X, which are A, B, C, and D, and the elements of Y, which are X, Y, W, and Z. And our function f is defined by this relation. Image of A is Y, image of B is G, and image of C is W, and then image of D is G. Okay, and then here you can see that X is not the image of any element in X. That means the inverse image of X is going to be the empty set, or inverse image of Y is A, inverse image of W is C, and inverse image of G, that's gonna be two element set B, D. Okay, we have a function f from X to Y which is defined like this. Now we want to investigate whether this function is continuous or not. Now, if this, according to definition, if this function is continuous, then what you have to have here is the inverse image of each element of this topology tau prime. That's gonna be one of the element in tau. Now let's take a look. First element is empty set, and the inverse image of empty set, that's gonna be empty, so it's obviously here. The inverse image of let's take a look, the inverse image of this singleton set. We'll come back to the inverse image of Y. So the inverse image of empty set is already empty, and the inverse image of let's take a look, that inverse image of this singleton set. Now you can see here X is not the image of any element here, so this is the empty set, and which is obviously here. Let's take a look the image of another inverse image of another singleton set Y, and you can see here Y is the image of A, so the inverse image of Y is the singleton set A. Now this singleton set A is in the topology. You can see singleton set A is in the topology tau. So that means the inverse image of this guy is open in tau, or is one of the element in tau. And similarly, we can find the inverse image of that guy XY, which is, now you can see from the diagram, the inverse image of X is nothing, right? And then inverse image of Y, which is again A. So the inverse image of this open set in Y is the singleton set A. So this is also fine. And then now finally let's take a look inverse image of the last open set, which is this guy. And now we can see from the diagram, Y is the inverse image of this Y is A, and then inverse image of G, which is there are two inverse images, B and D, and then inverse image of W, which is C. A, B, C, D, that is in whole set X. So the inverse image of this open set Y, G, W, that is the whole set X, which is one of the element in tau. And then finally, so we found the inverse image of each one is an element in tau, and then now we can take the inverse image of Y. If you take the inverse image of Y, that is obviously is going to be the whole set X. So for this function, we see that the inverse image of each element of tau is an element in tau. So that means this function f is continuous. Okay, then we can say that then f is continuous, then f is continuous since the inverse of each member or each element in tau, inverse of each member of tau prime is a member of tau. Okay, that means inverse image of each element in tau prime is going to be one of the element in tau. That's why our function f is continuous. Second part of the same example. Now here I'm going to give you a function which is not continuous. In first part I gave you an example of a function which is continuous. Now next I'm going to give you an example of a function which is not continuous. Let's consider a function g is from the set x to y defined by g of a, image of a is x and image of b is y. Still our x and y are same as in the first example, and the image of c, which is g, and the image of d, that's gonna be w. So let's take a look using the diagram here. Our function g is defined like this. Element of x, which are a, b, c, and d, and element of y, which are x, y, x, y, w, and z. And then our function f is defined by the image of a is x, image of b is y, image of c is z, and image of d is w. So this is how our function has been defined. Okay, so let's investigate whether this function is continuous or not. If it is continuous, the inverse image of each element in tau prime, it has to be one of the element in tau. Okay, let's take a look on the element of tau prime. Inverse image of this empty set, that is going to be empty, so which is here, that is fine. And the inverse image of y is going to be the whole set x, which is here in tau, that is fine. Now let's take a look the inverse image of this singleton set x. Okay, inverse image of that singleton set x. Now you can see here, if you look at the if you look at the diagram, inverse image of x is a. That's the singleton set. Now let's see whether this is in tau or not. Is in tau, that's fine. Now let's take a look the inverse image of the other element of tau prime, which is the singleton set y. So the inverse inverse image of y, you can see from this diagram, inverse image of y is the singleton set b. Okay, let's see whether this singleton set is in tau or not. Now you can see it's not in tau. That means, so here we found one element in tau prime whose inverse image is not an element in tau. So that this is not the so that g is not the continuous function. Then g is not continuous function, is not continuous since y, this is in tau prime. Now you can see here we have y in tau prime, but but G inverse of Y, which is the singleton set B, does not belongs to tau. Okay, so we found the open set in Y whose inverse image is not open in X, so that G is not continuous function. Okay, now here we define the continuous function, and we gave I gave two example, and one of them is an example of continuous function, and the other one is not. Now let me give you one more example of continuous function. Let's say X is a topological space. X is a topological space with discrete topology tau. So discrete topology means this is the power set of X, so where each singleton sets are open. That means each singleton set of X are in tau, and Y is the topological space with an arbitrary topology, with the arbitrary topology tau prime. Okay, X is the topology on X is fixed, which is the discrete topology, and the topology on Y is arbitrary topology. It could be any topology in Y. Tau prime, it could be any topology in Y. Then every function f from X to Y is continuous. Okay, it's continuous. Then now if we take any function from X to Y, that's gonna be continuous, because if you take the inverse image of an open set, let's say A is an open set, open subset of Y, then if you take the inverse image of this guy A, that's gonna be either that's going to be the inverse image of A is obviously that's going to be the subset of X, and we know that in the discrete topology any subset of X is in the topology. Since F inverse A, that is obviously is going to be one of the subset of X, but all possible subset of X, they are in tau. So F inverse A, it has to be in tau. That's why no matter what function you you take here from X to Y, if X has a discrete topology, no matter what topology you have in Y, that function is going to be continuous. It's continuous since for any open set H in Y, the inverse image F inverse, the inverse image F inverse H is open subset of X. Okay, so this is it's kind of popular example of continuous function in topology. Okay, now here we use the open set to define the topology. Okay, so if the inverse image of any open set in Y is open in X, then that function is called continuous. Now instead of open set, also we can study continuous function using basis for a topology in the given topological space. Now for that one I'm going to give a lemma. So this lemma it describes a continuous function using basis instead of open set. Okay, let's say we have x and y, these are still the topological space. A function f from x to y is continuous if and only if it is if and only if statement. A function f from x to y is continuous if and only if the inverse image if and only if inverse image of each if and only if inverse image of each member of a basis B prime for each member of a basis B prime for a topology tau prime in Y is open in X. Okay, so you can see this is if and only if condition. If you have a continuous function, then the inverse image of a topology tau prime in Y, it has to be inverse in X. And also if the inverse image of each basis element for the topology tau prime in Y is open in X, then that function is called continuous function. So this lemma, it describes a continuous function using basis element instead of instead of open set. So in fact the basis element itself is a open set. So this lemma is I think it's kind of obvious. If you use the proof of this lemma is kind of obvious if you use the definition of continuous function using the open set. I'm not going to prove this lemma, but I'm gonna give you some example of continuous function using the basis. Okay, example number 1. Let's consider the set of real number with standard topology or order topology, and the basis element for the standard topology on R, they are the open interval of this form. So these are the basis element. And then let's consider RL, or that's the set of real number with lower limit topology. So let's consider R with the lower limit topology. And the R with lower limit topology, this is the notation we have used in, I think that was in the first section. RL, that means the lower limit topology, and the basis element, they are those half open interval, left side included, right side not included. And the basis element for the standard topology, these are the open interval, both side not included. Okay, so we have those two topological space with their respective topology, standard topology and lower limit topology on R. Okay, in part A, then let's consider a function from a standard topology to lower limit topology, defined by defined by f of x equal to x, like kind of identity map. Okay, we have a function from R to R, and here R, the domain is or the first set is with the standard topology, and the second one is the lower limit topology, and the function is defined by this relation f of x equal to x. It's kind of identity map. Okay, for every, not exactly identity, but it's kind of identity map for every x in R. Okay, now let's see whether this map is continuous or not. So by that definition, since by the lemma is if and only if condition, right? If you go back to the lemma, it says if and only if condition. If the inverse image of the basis element for the topology in Y is open in X, then you can say the function is continuous, otherwise not. Now let's see whether we have that condition or not. Now let's take a look on the basis element for the lower limit topology. Basis element for the lower limit topology, they are in this form, half open interval. Now if you use this definition, then the inverse image of this set, or the inverse image of this basis element, since our function is kind of identity map, so the inverse image of this guy is gonna be itself. Okay, it's going to be half open interval itself, but this half open interval is obviously is not open in standard topology in R, because each open set in the standard topology, they are like the open interval. So now here we found that this guy is a basis element for the lower limit topology in R, but its inverse is itself, which is the half open interval. In the half open interval, they are not open in the standard topology on R. So that means this function does not satisfy the condition of our lemma, so our function is not continuous. So here, let me just write down the things that I just described here. Then f is not continuous, function, since the inverse image of a basis element, AB for the lower limit topology equals itself, like I describe here, and which is not open in the standard topology on R. Okay, that's why our function is not continuous. Okay, now here in this example, you can see here our function is from standard topology to lower limit topology. Now let's flip it and define the function like that. So what I mean here is, let's take a function from lower limit topology on R to standard topology and defined on the exact same way here, defined by f of x equal to x for every x in R. Now let's see whether this is open or our function is continuous or not. Okay, if it is continuous, according to that lemma, what you have to have is inverse image of the of a basis element in the standard topology on R, it has to be open in lower limit topology. And we know that the basis element in the standard topology or basis element for the standard topology on R, they are the open interval of this type. And if we take the inverse image of this interval, since our function is kind of identity function, so its inverse image of this interval is going to be the open interval itself, and this open interval is open. I mean, this is a basis. This interval is open in lower limit topology. This open interval is open in the lower limit topology. So you can go back to the definition of lower limit topology. You can see that this interval, those kind of open interval, they are open in the lower limit topology. So here we found that the inverse image of a basis element for the standard topology on R is open in R under the lower limit topology. So our function is continuous. Okay. So here the position of those R here, it does matter. So if your function is from standard topology to lower limit topology, defined by the same relation, is not continuous. But if your function is from lower limit topology to the standard topology, and then that could be a continuous function. Okay, then defined by this relation, then f is continuous. F is continuous because, like I described here, because the inverse image of then the inverse image of a basis element AB of the standard topology is itself, and which is open in the lower limit topology. Okay. All right. So here I give you two examples of continuous function using basis. First one is not continuous, but the second example of continuous function. Okay. Now here, so far we describe continuous function using open set and also using the basis element. Instead of open set and basis element, also we can study or we can describe continuous function using closed set. So for that we need a theorem. So I'm gonna give you a theorem, and that theorem describes continuous function in terms of closed set. I'm going to give a statement or the theorem without proof, and if you are interested in proof, you can take a look in Munker's book. Okay, and the statement is here: a function f from a topological space X to another topological space Y is continuous. It's continuous if and only if the inverse image, instead of inverse image, if you want, you can simply say the inverse. If the inverse image of every closed set in Y is closed in X. Okay, so this theorem, it tells us that a given function f from x to y is continuous if you take the inverse image of each closed set in y, and if that inverse image is closed in x, then the function is continuous. Again, I'm not going to give a proof for this theorem, but if you are interested in proof, please take a look in Munker's book.